Dear students, Assalamu alaikum. So this is lecture 18 for Fluid Mechanics 1 MEE 225. Uh, Today we are going to start chapter 5, that is finite control volume analysis. Actually we had already started chapter 5 in the last lecture when we derived the law of conservation of mass, or specifically we call it continuity equation in fluid mechanics. Uh, Apart from the start of the new chapter, or actually the review of the continuity equation is already part of chapter 4. So we'll first do a review of continuity equation and some examples of continuity equation. So this is how we derived the continuity equation in the last lecture. We started off with the Reynolds Transport Theorem, that is equation 4.19 on page 183 of your textbooks. So we said that we assume the extensive property to be the mass and the corresponding intensive property, that is lowercase b, will be equal to 1, and we replace b and b in the Reynolds Transport Theorem, and this is the equation that results from that. So the first term in this equation is actually time rate of change of the mass of the coincident system. The second term is time rate of change of the mass of the contents of the coincident control volume, and the last term is net flow rate of mass flow through the control surface. We already said that this net mass flow rate is taken positive outwards and negative into the control volume, and that is because of this dot product and dot product between velocity vector and the unit normal of area, that is n hat. So we have already have defined n hat earlier as well, but here you can also see n hat in this figure. It points outward on both the surfaces. So here it points outward of the control volume, here it points outward outside to outwards to the control volume, and over here it is normal to this control surface. Over here n hat is normal to this control surface. So with by definition the by definition of the system is actually system is defined by matter of fixed identity. This means that the matter or the particles that are inside the system, they don't change, so their mass cannot change. So the mass of the system does not change over time. That's why dmc over dt in this equation, it will be 0 in this equation. This will be 0 in this equation. So with this being 0, the continuity equation that we have comes out to be this. We had seen this equation in the last lecture. Further, we said if we can assume the flow to be steady and one dimensional, or actually steady and one dimensional, that is a uniform velocity profile over the area A, then we can change this integral to summation, and then this term, or this integral term, that is integral over cs rho v dot n hat dA, can be written as summation over the control surface rho v dot a. And if the flow is steady state, the term dava over dava t rho dv will be 0, because this means that if the problem is steady state, then the rate of change of mass of contents of the constituent control volume does not change, and they will be 0. then we can write it as rho VA out minus rho VA in. So all the inlets will be subtracted and all the outlets will be added together. This means that mass flow rate out minus mass flow rate in should be 0, or mass flow rate out is equal to mass flow rate in. So the law of conservation of mass, or the continuity equation for steady one-dimensional flow is m dot out is equal to m dot in. Same goes if the flow is incompressible, then rho in is rho out. In that case, we have a volumetric flow rate at the outlet is equal to volumetric flow rate at the inlet. Now we see an example for the continuity equation. Here we have a flow device that we can say, yeah, here we have a flow device. We don't know which device is it or what does it do, but we know that the fluid this device works with is water. So we have basically three inlets or outlets in from this device. One is inlet from the of the device, two is outlet of the device, and three is also outlet of the device. So at section 1 inlet, the dia is 3 inches. At section 2 outlet, dia is 4 inches, and at section 3 uh, outlet, the dia is 2 inches. Okay. uh, and at section 1 we are being told the velocity of the system. We know the velocity at section 1, we know the volumetric flow rate at section 2, and we know the mass flow rate at section 3. Okay, so what we are being asked is, we are being asked to find dm over dt, where dm over dt is the rate of change of mass inside this device or inside this system. So what we say is, we write continuity for this problem. Continuity for this problem is we write continuity for this problem to unsteady continuity equation for this problem, where the time derivative is not 0, because we know what we want to find out is dm over dt. So this is definitely going to be an unsteady problem. So we write that equation, and this equation is written as d over dt integral over the control volume rho dv, where this rho dv term is mass of CV contents, and integrated over the whole control volume. This will give us the mass of whole CV contents, and this is a summation over the control surface of rho v dot a. So this is the summation of fluxes through the control surface, or what is flowing in minus what is flowing out. So this will be the mass of the control volume, and this will be dm over dt. This term will become dm over dt, and this summation cs rho v dot a is still like that. Okay. Yep. So next we say, okay, mass flow rate is defined as rho AV, and we know that we have to find out mass flow rate over here to calculate to find out dm over dt. So because this term is just the summation of all the mass flow rates uh, in and out of this control volume, we should have probably drawn a control volume as well. We could have drawn a control volume around this device. I will try to draw a control volume over here with the pen, probably starting over here. This red line is the control volume. This might not be a very good drawing, but at least this will work. So the walls of the device are being included inside this control volume, and we are including the sections where we have either velocities or mass flow rate. So you can say that this red line actually defines the control surface. Okay, so the mass flow rate, we only know mass flow rate at section 3, where the mass flow rate is given as 0.3 slugs. At section 2 we have volumetric flow rate, which is 0.3 feet cube per second, and at section 1 we have velocity given, which is 30 feet per second. So mass flow rate is given as rho AV, and summation of all the mass flow rates across the surface summation over CS rho V dot A is equal to summation m dot out minus summation of m dot in. So m dot 3 plus m dot 2, because m dot 3 and 2 both are outlets, so they are both positive, and so m dot 3 and m dot out, m dot 2 both are outflows, and they will be positive, and m dot in will be negative because this is an inflow. So we know m dot 3, this is 0.3 kilogram per second. For at the section 2 we know the volumetric flow rate q, that is 0.3 feet cube per second. We'll multiply it with the density of water, that is 1.94 in British gravitational system, and this will give us the m dot 2, which is the mass flow rate at section 2. To find out the mass flow rate at section 1, that is the inlet, we multiply density with the cross-sectional area of the section and into velocity. This will give us the mass flow rate. This mass flow rate is minus 1.975. This is minus, so this means that net mass flow rate, this is the net mass flow rate, this is into the control volume, because by definition or by convention outflow is taken as positive, so this means that mass is accumulating inside the system. So now we again just have a look at the continuity equation that we had written earlier. This was the m over dt plus summation of mass flow rates over the control surfaces is equal to 0. So now the summation of mass flow rates over the control surfaces has come out to be minus 1.975. So the summation, so the rate of change of mass of the control volume, dm over dt, is equal to 1.975 slugs per second. So this is positive. This means that there is mass being accumulated inside the control volume. Okay, so we move towards another example. In this example, we are being told that water is entering this tank over here with a velocity, with a uniform velocity v is equal to 4 meter per second. The dia of the inlet is 5 centimeter. This is a circular cross section, 5 centimeter dia. Then it leaves the system, or it leaves the tank with a triangular, seemingly triangular velocity profile or a linear velocity profile. The dia at the outlet is 8 centimeter. The maximum velocity of the center line, this velocity, I should probably highlight it again. The maximum velocity, this velocity vector at the center line is defined as v naught, and we are being asked to find v naught. We are being told that this flow is steady. So Yeah. So to find out V naught, we must first draw the control volume around this system. So the dotted line that you can see in this figure, we have drawn the control surface around the tank, and the sections this control surface, it cuts through the sections where we actually know the velocity. So we know velocity at section 1, and it cuts through section 1. We don't know velocity at section 2, and our unknown v naught is at section 2, and it cuts through this section 2 as well. So we write continuity equation same as before, but as the problem is steady state, so dm over dt will be equal to 0. So assuming incompressible, because this is water, we can safely assume this to be incompressible. Assuming incompressible, summation of rho v dot a over the control surfaces, with this being incompressible flow, we can just say that this is equal to q1 is equal to q2, that is volumetric flow rate at section 1 must equal volumetric flow rate at section 2. So the volumetric flow rate at section 1 will be written as V1A1, where A1 we will calculate the cross-sectional area using dia is equal to 5 centimeter, and for section 2, the volumetric flow rate at section 2, we know that this velocity profile at section 2 is not is not uniform. This is a non-uniform velocity profile, actually a linear velocity profile. So we'll have to integrate from r is equal to 0, which is over here, to r is equal to r naught, which is 4 centimeters. So if we integrate from r is equal to 0 to r naught, we call this velocity as vr, this linear velocity from r is equal to 0 to r naught, we call this vr. And if we note that v2, actually we have represented v2 as vr, and vr can be written as a function of v naught and the radius r over here, and it is written like that, v naught into 1 minus r over r naught. So to calculate this integral, we have to define what is this area. How to define this area? We see this figure. Okay, so we have to integrate over this circular area, and the incremental area dA is the area where we can assume the velocity vr to be constant over the whole area. So what we do is we say, okay, we take a very small length dr at a distance r, and we draw two circles that are just dr apart in terms of radius, this length. So from center to this circle, the uh, distance is represented by r. R naught actually represents the full radius of this pipe, and this shaded area dA is actually the area where we can assume the velocity to be constant. If we stretch it out, this becomes a rectangle, and this rectangle has a length of 2 pi r. R is the radius of this shaded area. Because this dr is very small, so we can assume both these lengths, this length and this length, to be equal to 2 pi r, and the area will be 2 pi r into dr. So that's what we have written over here. So v1a1 will be equal to integral from r is equal to 0 to r naught of vr 2 pi r dr, and putting in the values, that we have the final answer. V naught is equal to 4.69 meter per second.